So the first programming project blink an LED once per second. That's using AVR assembly. Now, when presented a problem in basically software development or engineering in general, you are given two things: a starting point, what you have to work with, and the end goal of the problem to be solved. What is the desired result? Okay, and in other classes I've discussed this. I just forgot about it and didn't do it for this programming assignment. When you have both the starting point and the end point given to you, you can approach the problem from the beginning and from the end. Now, the idea is to start with what you have. What can you do with it? Ask yourself, what can you do with it? In the case of you're using an AVR assembly with the processor that we're studying, what can you do with it? Too many things to count. It's kind of, overwhelming what you could do with that little piece of silicon. But you have a very specific end result. Blink an LED once per second. So, starting from the beginning isn't very practical in this case. Start from the end. How do you start from the end? You ask yourself the question over and over again, what do I need for that? Okay. So you work from the end backwards, asking, what do I need? And what can I do with this is from the beginning. Now, from working from the end, something that I do a lot with when I'm writing software is what I do is I use index cards. For every index, for every result, write it down on an index card. And then you and then underneath that, answer the question, what do I need? List off what you need to accomplish that end result. Okay? So, let's go to a clean page here. What do I need? What do you need to blink an LED once per second? An LED, yes. What else do you need? A clock, yeah. Something to tell time. Anything else? A connection.
So maybe like some type of, we're using APR and stuff.
Yeah, but we're developing that. So what you need is an LED, tell time, and a connection. Okay, so as it happens, the Curiosity Nano board has one built in. So that's taken care of. How do you tell time? With a timer. As it happens, the processor has timers. So use a timer. It's the name of the board that the processor is soldered to that I use for testing circuits and programs. Yeah. I need to put a link to the Curiosity Nano board where you can purchase it if you so choose. They were thinking about getting the department to pay for a bunch for everybody, but I haven't heard anything back on that. So use a timer. Okay. Connection. How do you connect a LED to the processor? Well, through it. Well, I was thinking more in lines of through a GPIO port. Yeah, a wire, yes. But what's it connecting to between the processor and the wire? It's called a general purpose I/O port. Now, the built-in LED is on port C, pin 7. Has the LED. Okay. So that takes care of the wire, and it tells us which GPIO port that we're going to be using. Okay. So that's what you would have on your first index card. Okay. Now you take each of these that you don't that aren't checked off and start another index card. Okay. So tell time. What do you need to do to tell time? Yeah, what do you need to do? How is time calculated? So that is determined by the type of timer.
Not like a minute, hour type time.
Well, there's the processor has what's called a real-time clock timer that has potential. So we'll revisit that, and then we have the what else? What else do we need to do? We need to configure the timer for our use. And what does the timer produce? It produces interrupts as the output for the timer. It triggers interrupts at different intervals depending on the configuration for the timer. So you need to handle those interrupts. All right. So just from the name, the real-time clock timer seems like a good candidate. So we'll go ahead and choose to use that. Real-time clock. And then again, the that one's checked off. Then you have the configure timer for use and handle interrupts. Well, again, go to the next level of index cards and title the two more index cards, configure timer and handle interrupts. Okay? So, configure timer. Okay, let's see here. I have the whatchamacallit? And we will go to the timer. Oops. There we go. There we go. And we'll go to the timer in the table of contents. It has, come on, where are you? Brownout detector, voltage reference, watchdog timer, timer counter A. That's not the real-time counter. B, C, there's the real-time counter. RTC. And the section is only 24 pages long, so it shouldn't be too terribly complex. We'll go to that page. It has 16-bit resolution, selectable clock sources, programmable 15-bit clock prescaling, a compare register, a period register, and periodic interrupt and event is generated. Okay, so RTC counts pre-scaled clock cycles in a counter register and compares the content of the counter register to a period register and a compare register. The RTC can generate both interrupts and events on compare, match, or overflow. It will generate a compare, interrupt, and or event at the first count after the counter equals the compare register value, and an overflow event or interrupt and or event at the first count after the counter equals the period register value. The overflow will reset the counter value to 0. So, the reference clock is typically 32.768 kilohertz. Pretty precise. That means it's 15? That's 15 bits, right? 2 to the 15th is 32,768. Oh, you can do that in your head, right? Somebody got a scientific calculator handy? Yeah. 32,768. So 32,768 clock cycles for 1 second. Sounds like easy math. Just put a 1 in the 32Ks slot of the period register, and you got your period of 1 second. Okay? Seems pretty easy. Let's skip all the functional description. Oh, here's the configure the clock. Configure the desired oscillator to operate as required in the clock controller peripheral. Get back to that in a little bit. Write the clock select field bit to the clock selection register accordingly. And then you configure the RTC itself. Set the compare value in the if you want to use the compare value in the compare register, and the overflow value in the period register. Enable the desired interrupts by writing the respective interrupt enable bits in the interrupt control register. Configure the RTC prescaler to the desired value. And finally, enable the RTC by writing it to the peripheral enable bit. Writing a 1 to the peripheral enable bit. In the let's see here, it gets more timing and debug operations, all this. Here we go. The register summary. It mentioned the prescaler. That's in Control A. Real-time clock enable bit. It's in Control Register A. Interrupt control bits to determine whether or not a interrupt is enabled. The period register, the count register, the compare register. All of them are right here that were mentioned in the initialization section. So what is the let's go back to there we go. Oops. Let's do the clock control. It mentioned the clock control. Well, let's go back to the configure the timer. Take this step by step. Configure clock control. And in the timer itself, we will set the period. We will enable interrupts. Yeah. What else was there? Set the period. So and compare. Because you need two different events, two different interrupts for this, right? One to turn on the light and one to turn off the light, right? So we'll have one for the period and one for the compare. We'll set the compare to turn on the light, and the overflow, the period value to turn off the light. So there we go. And that's to configure the timer, and finally enable the timer. Enable the timer finally. That was basically the three things you needed to do for the timer, right?
For the period and the compare, is there some timer clock and then we go down
Yes. The interrupt handling routines will turn on the light and turn off the light. So that
essentially it's like giving a period and compare place what's actually action.
the interrupt handling routines are doing the actual action. Yes. So if you look at the count over time, the count counts up, right? And you set this is the count value. And then you have this period value. And when count value reaches the period value, it triggers an overflow interrupt and resets count value to 0. And it starts counting again. Reaches the period, triggers another interrupt, drops to 0, and so on. What the compare does is the same thing as the period register. It triggers an interrupt when the count gets to a certain level. So when it gets to the halfway point, in our case, it will turn on the light. And the count will still be counting up. It doesn't reset to 0 until it reaches the period value. It'll trigger the period the overflow interrupt and then reset to 0. So the light will be off, on, off, and then off, then on, then off, like that. Yeah, that's how the timer will work. Simple enough, right? We'll get to the configuration when we get to it. But take it piece by piece. Yeah. Yes. From here to here is 1 second. That's where we're configuring the clock to be. So, yes.
So I noticed that. So the light is turning on when
the compare value reaches, when the count reaches the compare value. Yes.
So, and we also like program this too. Like the light turns on when it reaches a peak value instead of a complete value. Why are we doing this way?
So you would have it turn on at this point, and then what would happen here?
It should be on there.
It would be on here, and all along here. What would it do here? Should turn off. How do you distinguish when it gets to that point? How do you distinguish whether or not it's on or off? Which one to do? So instead, have two separate interrupts. One, all it does is turn the light on. The other one, all it does is turn the light off.
Those values are still considered, but they're still interrupts. They're considered interrupts?
Yes, they are interrupts. An interrupt is a hardware triggered process that interrupts the flow of the normal program, jumps to an interrupt handling routine, and then returns from it back to the normal flow of the program.
Our case would be this all the way up until period value.
Well, in this case, the normal flow of the program will be doing nothing. It'll just be going in an endless loop. Yeah, that's the. This is purely interrupt driven. There is no other program going. But yeah, you have the loop going here, and then the interrupt jumps out, runs a program, it runs an interrupt handling routine, and then jumps back as when the interrupt it gets triggered. So All right, let's go back. Oh, did you need something?
I forgot that you, are you gonna, I remember that.
Yeah. But anyway, so we go back to, so we got the configure the timer, and then handle the interrupts. And I was just talking with this fellow up here. Where did he go? Oh, okay. We're almost out of time here. So, handling the interrupts. How should we handle the interrupts? There's two of them. Turn on and turn off. What should we do to handle the interrupts?
Well, I mean, it looks like a flag that you just showed on positive is and off. Positive again.
When you have the compare, it'll turn on. When you hit the period, it'll turn off. Yeah. So it's just a matter of first of all, some housekeeping. Turn off interrupts. You don't want your interrupt to be interrupted, right? So turn off interrupts. There's a flag that gets triggered when the interrupt is triggered. Or I should say there's a flag that triggers the interrupt. You have to turn that flag off. Otherwise, it gets triggered immediately again when you get out of the interrupt handling routine. So turn off flag. Okay. And then that's the housekeeping that we need to do. So just all we need to do is turn on port C, pin 7. And then turn on interrupts again, as we're done. So there you go. That's all there is to the handling routine. To turn it on. To turn it off, basically it's the same thing. Just turn off the off pin. That's all you need to do is turn off the interrupts, turn off the flag that brought us there, turn on the pin, and then turn on the interrupts again. Turn it off, do the same thing, except for instead of turning it on, you turn it off. This is one line of code. This is about 2 or 3 lines of code. This is Depending on how you do it, it can be up to 4 or 5 lines of code, and turning on interrupts is 1 line of code. Yeah, for 4 steps. So it's about 10, 12 lines of code, somewhere on there. So, yeah.
So you said only turn off and change.
Yeah, between these two, only turning off and turning on would change between the two interrupt handling routines.
Assuming that these two happen, like, turn off, then turn off, turn on, then turn off, right? The last step of turning on is that it switches on the interrupt.
Yeah,
But for the beginning of turn on, it turns it off. So what did it turn on the interrupt here so that it's turned off?
yeah. You would turn on you would turn on the interrupts after turning off the pin. Let's see here. Yeah, turn on interrupts.
This is for off.
Yeah, but you turn on that. You do that. Turn on the interrupts.
Okay.
Yeah, after the interrupt is done,
Okay, yes.
you turn on the. That just about wraps things up for today. Wish I had a little bit more time. Get to the fun stuff, the actual writing code. But you can see from here, you would take your index cards, turn off interrupts, write your line of code for that. Turn off the flag, write your few lines of code for that. Turn on the port pin on a different index card. Each on an index card, you would have your little code snippet of 3 or 4 lines of code. And then you assemble them and take things in bite-sized chunks. And then you assemble them together into the final program. Okay? All right, well, that'll be it for today. Running out of time. So have a good day. See you on Wednesday.